Yeah, I guess some of you might have noticed that I'm playing a background music. That is from the Maple Story, one of the games. And you know what? One of the important, yeah, good, very good. Shen Hao is Howard. So one of the creators of the Maple Story, it's a very popular online game which is not 3D and yet very popular. So one of the creators passed away last week, just after we started talking about games. And by the way, games are probably the most used applications, network applications currently. All right, yeah, good morning, Jia Hong and Shen Hai. Now let's go ahead and start the lecture today. We do have several topics, but before we go into there, let's go through the announcements. So this week, we do have 4 quizzes due from 9 to 11. So the quiz today is going to be a little bit challenging, a little bit more open. You need to argue for your choices. And but on the other hand, for quiz number 10, 11, no, so it should go. Sorry, it's quiz 8 to 11, not 9 to 11. I'll correct that later. So the quiz for today is number 8. For tomorrow, we have 9, 10, 11, but those quizzes are straightforward. All right, so this week, lightweight, we have only 4 quizzes due, no PA, yay. But you know what? Don't be too happy about it because PA number 3 is due next Saturday. And PA number 3 is the first PA you need to start using Socket. Okay, so it's not exactly straightforward. And you might want to start working on it earlier. So pollys server is not yet on, allowing you to test your PA3. It will be turned on later today. All right. Oh, there are more of you showing. All right. So let's see. Amelia, Youyu, Xuehan, and Zewei. There's just one thing I would like to draw your attention. I think from your ntu.edu.tw email account, you should be seeing an email generated from Google inviting you to a shared Google spreadsheet. That is our grade progress this semester. Okay, and Polly will be updating that spreadsheet every 2 weeks or 3 weeks, depending on when will be the best time to take a break. So now we are the 4th week into the semester. So I have actually recorded all the grades for the first 3 weeks. So you can check those out and get a rough idea whether you want to, turn up a notch participating either on Slack or on YouTube channel, or feel free to call in from the Google Meet. By the way, Catfish here has called in a few times. He's got quite a few questions to ask. Okay, so hey, Catfish is the only one earning the office hour points. So make sure that you use whichever form that you prefer. And by the way, for each of the YouTube channel or Slack, I only know up to 5 for each week. Okay, so I'll try to rotate and get used to all these different platforms so you can do interaction with me or interaction with the class. All right, so that's what I want to say. In case you missed that email, let Polly know. I'll have Google send that email again. All right. If you have trouble reading, if you have trouble navigating the Google spreadsheet, or if you are disallowed access to the Google spreadsheet somehow, you got the email, but you click into the link and somehow didn't get in, couldn't see your grades, also let me know. Okay, good. And the topic for today, let's first wrap up section 2.1, which is the opening section of chapter 2. Okay, Last week, let me try to recap. We talked about a few things before one can design a network application. Okay, so before you start designing, you need to think about what kind of communication architecture or communication model you want to use, right? A very classic model, client-server. And more recently, recent years, people started to do more and more peer-to-peer model. Okay, so I think it has something to do with how you are planning to build the server cluster. Are you prepared to invest a lot of money into that? Or you want to invest just some, and you hope you draw in resources from your customers as well, from your users as well, so that you can share to some degree. Then you might consider a hybrid, right? Hybrid communication model or hybrid architecture. So that is one, architecture of your application. Number two, you need to start build a socket, right, to connect the programs, either on one peer to another peer side, or from the client side versus the server side. So there'll be programs running on different end hosts on the internet, and you need to create socket to connect these programs. And the messages you send through the sockets, you need to define, right, what types of messages there are you're going to send. What is the format of the messages, and if you receive one message, what is the next message you generate and respond to the sender of the original message. And we ended up talking about QoS because to establish the socket, you need to specify in the socket what port you want to use. And you want to specify also what kind of transport layer service you want to use, because there are multiple types. And which type you use, it depends on this thing, QoS, quality of service. And we talk about 4 quality of service, if you recall. First is you ask yourself, right? Would your user expect no packet loss or not? Okay, is ensuring that packets always arrive at the receiving end important? Is it gonna hurt? Would the users complain? Second, delay, right? Would the delay complain if would the users complain if the delay is too long? And third, what? In case you're transmitting, for example, video, the volume of data is high, so you probably want to worry about whether you can guarantee certain throughput, right? And what is number 4? Security. So the rest of today is that first is to try to wrap up QoS. Now, how do you know for your application what kind of QoS you need to supply, you need to provide? So next video here is to go through some examples we know already, and what kind of QoS the designers of these apps expect from their users. Let's go over a few common applications and see if we could sort out their quality of service requirements, or in short, QoS requirements. First application, file transfer. Transferring files are static objects, most of them text-based. Therefore, in terms of data integrity, we demand 100% reliability. File transfers, we do not expect they arrive in a few seconds. Okay, so it's not delay sensitive. As a result, there's no strict bandwidth requirement. Therefore, the throughput part of the QoS, elastic. You can probably imagine email and web objects. These are transferring also files, email files, transferring web pages, okay, web page files. Therefore, the QoS requirements very similar. The second application here is real-time audio video. So, first of all, the nature of content, audio video, different from text. Therefore, keyword, non-text, it can be delay tolerant. Okay. Another is it's real-time, that means it's interactive. That's another keyword, which means we do have delay requirement. And for real-time, that's showing the audio, video that's happening right now. So the delay needs to be less than hundreds of milliseconds. So you feel like it's happening right now. Audio, video, now there's time sensitivity, therefore we need to maintain minimum bandwidth. So there's a bandwidth requirement. And the requirement for audio, lower, video, higher. These days, some users might actually expect even higher bandwidth for video. Now, can you think and push a little bit and see if you know the QoS requirement for stored audio video? Well, first of all, keyword audio video non-text, therefore, you can probably guess data loss here is loss tolerant. What about the delay requirement for stored audio video? It should still be some requirement, but probably not as strict as the real-time audio video. And you're right. Delay can be a little bit longer. But given that there's delay requirement, the throughput is still hard. We still need to make sure that there's a minimum amount of bandwidth available. And audio video, the bandwidth requirements are because of the nature of the content. So it will be the same. Audio, 5 kilobits per second to a megabits per second. Video, 10 kilobits per second to 5 megabits per second. Now what about this one? Yeah, interactive. The keyword is similar to the real-time nature of this application, isn't it? Except that this is now game data. So you can imagine, oh, delay requirement here, just as strict as real-time audio video. Is it loss tolerant? It's a little bit tricky, isn't it? What about throughput? If there's delay requirement, then there's usually a throughput requirement, but it should not be as high as video or even audio. So here, just a few kilobits per second. Game, this part is debatable. For some games, for example, shooting game, some of the players would argue, I want no packet loss. Okay. But for most of the interactive games, it's okay to have some loss. Okay. And then the users, the players, can try to repeat actions to make it up. What about text messaging? Keyword text, so no loss, obviously. Throughput? Yeah, it depends a little bit on the delay sensitivity, isn't it? And text messaging these days, yeah, it's also debatable whether it's time sensitive. Some will say yes, some will say no. Okay. But you see also that the delay we experience in text messaging, most of them are probably thinking delay, not network delay. Okay. All right, so you see now, in order to find out the QoS for the application you're designing, you will have to actually think and maybe debate or discuss, or maybe doing a user survey to get a better idea. All right. Next, transport layer protocol. You can finally decide what transport layer protocol for the socket. But let me introduce the transport layer protocols first. In order to find out what is the right transport layer protocol for an application, we also need to know what the options are. We do have two, TCP and UDP. TCP is the one more elaborated. UDP is very primitive. Let's focus on TCP here. The reason it's more elaborated is because it provides reliable transport. Think, a sending process and the receiving process. If we connect the two of them using a TCP at transport layer, data will always come to the receiver 100% correct. There's not going to be error. There's not going to be lost packets. How do we do that? Well, let's talk about that in Chapter 3. In fact, that's the main content in Chapter 3. For now, keep in mind, TCP provides reliable transport, no data loss. Second, TCP also does flow control between sending process and receiving process. The sending process here is checking whether the receiving process is busy or not. In case it's busy, the buffer gets full because data comes to the receiver and gets buffered temporarily here. If the receiving process is a little bit busy, the speed that we extract the data out to the application could be slow, so buffer builds up. If the sending process is sending data too fast, those data arriving to a full queue, full buffer, data get lost. If TCP is doing all it can to try to recover from loss, it doesn't make sense that sending process is sending data too fast to create data loss. So, flow control, some sort of communication going on between the receiving process and the sending process so that the sending process will slow down. Congestion control, it's a little bit similar to flow control, but it's between all these other routers in the middle of the path from the sending process to the receiving process. In case any of the buffers, okay, in the middle on the internet is close to full, sending process slows down. If the buffer is no longer full, packets can go smoothly, speed also comes back up. Okay, so that is called congestion control in TCP. This, in fact, is also one of the main content that we'll talk about in Chapter 3. So for now, just keep in mind, TCP does reliable transport, flow control, congestion control. TCP, however, does not do this. Timing guarantee, minimum throughput guarantee, security guarantee. So the other three QoS requirements we talked about, TCP does not provide. The only QoS guarantee it provides is reliable transport. So this is TCP. Now there's one more feature about TCP. It's called connection oriented. To set up a TCP connection at the transport layer, the sender and receiving process also do some sort of control message exchange to set up a connection. So this part of internet, although it's a packet switching network, but the behavior is a little bit like the circuit switch network. And there's a reason for it. Okay? This is so that we have more communication so we could recover from errors. UDP, it does not do reliable data transfer. There's nothing really going, no more communication between the sending process and the receiving process. Sending process is send, receiving process is receive. It does not provide flow control, congestion control, none of these timing, throughput, security guarantee either. There's no connection set up. So this is really the native packet switching network transport layer service model. Okay. Now you know, TCP essentially does nothing. You're right. The question is, why do we bother having UDP? Why don't we just use TCP? Yes, if you recall, among all these applications we've mentioned, text-based content, we prefer reliable transport. But is there other kind of content that reliability is not necessary? It's okay to have some loss. Yes. Sending audio video is not necessary to have 100% reliability. So quite a few of these audio video multimedia services, multimedia applications, prefer using UDP as the transport layer service. All right, so there are two options, but before we go on and look at for a few example applications, which transport layer service they choose, let's come to the chat. So Xuehan had a question. Why do the text-based applications have this elastic throughput requirement? Okay, what do I mean by that? You see that these text-based applications, emails, web pages, do we expect that they arrive in real time? We typically don't. In fact, for emails, you don't really check your emails, right, all the time. And so that you never really expect text messages or, well, emails or web applications particularly, whether they need to arrive in a delay requirement. If there's no delay requirement, right, then there's not really a need to guarantee a throughput so that the data arrive within a short period of time, you see. Therefore, the throughput, there's no throughput guarantee, therefore it's elastic. Okay, so the throughput can be low or high. Okay, flexible, that's what I meant. All right, I hope that answered the question. But for video streams, volume high, and usually you expect that the bits arriving for video continuously. So you hope that the delay for a video stream is fixed. In order to guarantee that, you see that there's a need of a hard throughput guarantee. And so it will not be flexible, it will not be elastic. Okay, so just to contrast a little bit, hope that I answered the question. And now let's come back to transport layer. Which one do we choose? Let's go through also a few examples. Here, let's go over some common applications and see what transport layer protocol they pick. Email, well, in fact, remote terminal access, remote logging, such as the terminal you're using to remote logging, SSH to the PA server. Web downloads, file transfer, all these are what? Text-based, static objects. Reliability important, but it's elastic, no delay requirement. So, not surprising, you see them all using TCP. So these are just the specific protocol, okay, each of the application is using. Email is the application. The application layer protocol is called SMTP, Simple Mail Transport Protocol. For World Wide Web, this is the application. The protocol supporting World Wide Web is HTTP. File transfer, the protocol, FTP, standing for File Transfer Protocol. Now, these two other applications, streaming multimedia such as Netflix or YouTube Live, audio, video, reliability is no longer required. Therefore, you see, some streaming multimedia applications use UDP, but some stick to TCP. Internet telephony, Google Meet that we're using also on the side is one such internet telephony application. It's audio, video as well. So UDP, and sometimes some of these internet call services are TCP. And that takes us to the quiz today. So this is quiz number 8. What do you think? Should game use TCP or UDP? All right, and there are 3 games here. The one on the left you see is the Farmville. It's a web page game. It's a website game. All you do is to let the time tick, and you probably plant corn or orchid or carrots. So as the time ticks, they will grow. Then you can harvest the flowers or the crops. And your friends can come over to steal some of your crops as well. And as in return, you go to their farms and pick up their crops as well. So Farmville. Okay, so for this type of game, web-based, okay, not exactly interactive, would you use TCP or UDP to transmit game data? Now for the game in the middle, PUBG or shooting games in general, do you think this type of game should use TCP or UDP? And the one on the right, it's called RO. I think it's one of also very popular game, and it's the massive multiplayer role-playing game. So the pace of the game can be much slower. For example, you see here a group of friends, online friends. They probably just gather to chat outside of a town, and so massive multiplayer game, the role-playing games. You could have complex gameplay, chatting, or intensive raid, things like that. So for this type of game, role-playing game, massive multiplayer role-playing game, do you think you use TCP or UDP? Okay, so for each of these game types, discuss with your teammates. Okay, and you probably want to start thinking, would the users expect full data reliability, short delay, high throughput, and security? So for each of these 3 games, depending on how you find the QoS is, choose a transport protocol. So essentially you type up for Farmville, TCP or UDP, and why. For PUBG, TCP or UDP, why. For RO, TCP or UDP, why. All right, so let's begin. I see that several teams have already typed what you have up. Okay, so that's great. So Team 7 here, okay, is saying for Farmville, UDP is okay because it's actually just a very casual game, right? So packet drop delay, nah, doesn't matter. I see the thinking behind. PUBG, TCP, oh, a very serious game. Okay, of course, no packet drop and no delay. Okay, so they were hoping that using TCP, and there's not much delay with TCP either. Okay, interesting. RO, UDP, packet drop delay acceptable. Yeah, because role-playing game, unlike the shooting games, it's the pace is much lower. I guess that's what Team 7 had in mind. Okay, makes sense, right? So Team 7 kind of classify the three kinds of game based on how serious, or maybe Team 7 play more the shooting games, right? So need to be reliable and short delay. And for the rest, the pace is lower, so UDP doesn't matter. Let's see Team 1. Team 1 actually think a little bit different. Team 1 actually say for Farmville TCP. And the reason is that it's not real-time type. Oh, okay. So the keyword seems to be real-time or delay, short delay. So Farmville for Team 1, it does not require short delay. Good. So TCP does not really guarantee delay. And UDP being simple, usually the delay is shorter. So they pick TCP. Okay, good. So Team 1 actually focus on delay. This QoS requirement. PUBG, UDP. You want to have least amount of delay? Yeah. So you see that Team 1 and Team 7 both, okay, think that PUBG is a serious game. You want short delay, okay? But the two of them choose different protocols because Team 7 thought that packet drop is also critical, okay? It should not happen. But Team 1 thought that delay is absolutely something that's not compromisable. So pick UDP. And maybe reliability can be compromised a little. I don't know about how you play the shooting game. I tried a couple times. I'm not very good at it. Okay, if I fire and there's no action, then I fire again. So you kind of keep triggering and shooting. That human action itself sometimes retransmit for packet loss. Okay, so it probably sort of mediate the impact in case there's a packet loss or two. So UDP might make sense. It depends on how the playing style is. RO, yeah, as I mentioned, RO is a mixed role-playing game. So Team 1 here is saying they will use TCP and UDP mixed. Yeah, so it has multiplayer and single player mode. They guess, yeah. I think RPG game can be quite complex, different kinds of gameplays, right? So you can form teams and raiding a monster, or you can go shopping in a sort of a market. So all kinds of gameplays. So I guess there could be team play. There could also be single player play. So the point is, if you are playing some real-time multiplayer section of the game. Okay, so if you are doing team play, then the delay is probably important, right? Because you don't want to act slow and the other teammates are actually complaining about you being slow. But in fact, it's just the network being slow, not you being slow, all right? So you want to somehow ensure the delay being somewhat the same. And making sure that you can keep it in real time is another way of guaranteeing that no one perceive sort of reaction delay. We want to have a quick data transfer and less delay for this real-time part. But for a single play, if you're just shopping a market, then it doesn't matter what the delay is, so TCP will be okay. Okay, so it's very interesting. So team 7, team 1, very different perspective. So team 1 obviously here focusing on delay. Let's see, team 2. Oh no, what happened? Wei Yuan. Yeah, you're very interesting. Let's see, team 2, Zewei. You guys must be Zewei and Wei Yuan must be very good friends, I think. Game 1, so that's the Farmville. Team 2 chooses UDP because this game doesn't really need reliable transfer. It's very casual. Yeah, I understand. Small loss, data, delay should be fine. Okay, so the thinking is a little bit similar to Team 7. TCP, because the player will be angry. Yeah, of course. So again, I think the thinking is a little bit similar to Team 7. No delay, no loss. Okay, even stricter. Game 3, a role-playing game. TCP better. Still have some multiplayer interactions. So the pace is a little bit slower. It's probably not necessary to do UDP, and it would not hurt to guarantee reliability, right? Team 7. Okay, let me do this. Very good. Farmville and RO for Team 3, TCP. Not real time. Okay, you see, Team 3 is thinking more like Team 1. Yeah, PUBG UDP, real time. So Team 3 is also sticking to delay. And Team 8. Okay, so this is great. Let me just add this. Okay. Farmville TCP, not real time. Okay, so Team A think a little bit similar to Team 1 in Farmville. But for PUBG and RO, UDP. It's better that for these role-playing games and shooting games to make sure the delay is as short as possible. Packet loss might be tolerable, right? Because again, if you are just walking, you click to a location. In case you find your character is not moving to that location, you click again. I think there are some parts of the games that somehow the player will react naturally to recover for the loss. Interesting. You guys must have a lot of experience playing these games. I think for parts of RPG, indeed, okay, UDP better. But I don't know about the kind of RPG games that you can set up a shop there, right? It's probably not good to use UDP there because if there's a transaction between you and another player, if you pay the money, but the packet that's sending you the goods over is lost, then ouch. So I guess in that sense, Team 1 saying use both TCP and UDP for role-playing game makes sense. Because for that kind of gameplay, you don't want to miss a lot of game money there. Okay, so Team A, yet another opinion. Okay, so Team A is actually not exactly like Team 1 either. Very good. Okay. Farmville and RO TCP. Yeah, I guess this is throughput requirement low, and it doesn't need to. It needs to be reliable. Okay. Okay, so I guess for RO, if you are reliable, then the in-game transactions, okay, would not be a problem. For Farmville, I guess, Farmville can be a serious game for some people, right? So if you steal something or if you plant something, you expect that it actually is in your hands, okay? Or it will grow, the crops will grow. PUBG UDP because delay is absolutely important. So I think no question for shooting games, delay absolutely important. And if you can guarantee reliability, even better, right? So I think the QoS requirement for PUBG is quite clear. But you see that it's not exactly straightforward. Knowing the QoS, you get to choose the perfect transport layer support, isn't it? So sometimes for all these QoS requirements, you might need to compromise one for another. So it's not a clean cut, not exactly a binary selection. It might need to be. You might need to consider the trade-offs. And I guess Team 1 there, thinking a little bit more, it's probably not good either way, UDP or TCP for RO. So they decide to use a mix of these. Inside the game, you know what? For some message exchange, you could create a TCP socket. For some other message exchange, you can create a UDP socket. You can have two sockets between two softwares running on different end systems. All right, so wow, okay, so Team 5 for 14. Well, you know what? Polly will come back to go through you guys' solution for quiz A, but I think you get the idea. Okay, so let's come back to the last part of the lecture. Hey, there's one QoS called security, and if you follow the transport layer video, there are only two options, UDP, TCP, and none of them serve security. We do have an option, okay, called TLS. And then we start with a video introducing SSL, which is the prior version of TLS. All right, secure TCP. This is the next topic. Yeah, if you recall, when we were talking about these service requirements, right, there are four of them. Reliability, which is supported by TCP. Delay requirement, right, which is somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the fourth, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, and that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layers. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay? So it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential, okay? Because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank's server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message go through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, Ssl Socket Api. Yeah, to implement SSL, there are APIs available for each programming languages. In Chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there we'll be using this TLS, Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays people don't call the security support over TCP SSL. They are all referred to as the TLS. Okay. If you think about it, this makes a lot of sense because hey, SSL there is not really a layer. It's more a support for security. All right.
All right, so next, how TLS works.
Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key, and we share the key with Bob and Alice. So when Alice has a message to send, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key. Alice is yet to send the secret key to Bob, isn't it? I mean, didn't we need TLS because we fear we send password in clear text to the other end? So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send, and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble so this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the received message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensure secret exchange. So TLS illustrated up here works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from ENS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see Alice's one is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked.
All right. So one can actually use a socket that's TLS socket. In fact, PA number 9 is allowing you to exercise creating a TLS socket to transmit web pages. All right, so that's all the lectures for today, but let me attend to the 2 questions before you go. First, let me answer Zewei's question first. Does TCP have higher delay than UDP because of flow control? In a way, yes. Because in order to control the flow or to control congestion, the sender and the receiver end of the TCP need to establish a connection first before the data can be sent. So there's always an initial delay there. Okay. Unlike UDP, UDP just go ahead and send data without handshake, without hello first. So TCP initial delay always higher. Does TCP have smaller bandwidth than UDP? Usually yes. TCP has flow control or congestion control. That means there's like a window of a window of bandwidth allowed, okay, for a TCP connection. That is actually determined not only by how much resource, how fast the sender can send, but also all the routers in the middle of the network, because congestion might happen in the middle of the network. Okay, so how fast a sender can send data into a TCP socket depends on many things. And so the sending rate or throughput of a TCP connection can be limited by all these factors. But UDP just send. UDP doesn't need to worry about having packet losses. So UDP could send in very, very high speed, high occupying a lot of bandwidth, okay? And in the end, potentially higher throughput the receiver sees. Yeah. So generally, TCP having longer delay because of the connection setup stuff. And potentially, in case there's packet loss, there's a mechanism in TCP that's retransmitting. So those are also delaying sending of data. TCP usually the throughput lower than UDP because UDP has no limit. You can push and push and push. That's why nowadays many of the firewalls will just block UDP traffic entirely because some of the hackers actually do UDP, send traffic in UDP to do denial of service attack. When the traffic volume is too high, it might kill a router or kill a particular server. So I hope that answered your question, Zewei. And let me attend to Liang Xin's question, which is much earlier here. And hey, guys, you know what? The time is up. So feel free to come back to watch the last few minutes of the video in case you need to rush to other classes. Okay. And of course, feel free to go. So last question from Liang Xin is, why streaming multimedia does not require reliability? This is a very good question. Because you see, audio and video, if pollys speaks a couple words, you can still capture part of what I'm gonna say. You see, so human beings send audio, human beings send video. Receivers are also human beings. There's some sort of intelligence here already. It's okay to have glitches every now and then. Or a shortage, sort of a breakage every now and then. Also that the audio-video compression or encoding schemes are getting better and better. When we decompress, we can try to interpolate from nearby voices or nearby image frames in a video stream to recover from the losses. Okay, so audio-video, multimedia content, unlike text, is a little bit special. I guess in a way, if you send instant messages, if you missed a word or two, it doesn't hurt either. But in a short sentence, if you miss some keywords, and chances higher that human beings don't pick up exactly what they meant, what the sender meant.
Okay, and I hope I answered the questions. All right, so if you just couldn't stop and want to ask more answers, feel free to do so. Polly is gonna stay on for just a couple minutes, but with that, I think feel free to go. Go catch the next class. Okay, bye guys. Or go out there. Yeah, the weather is so nice. Okay, bye, Sean. Okay, bye, team. And hi, Jiahong. Jiahong, I know you, right? The name looked really familiar. Bye, Yujie. Yeah, so Polly will spend the rest of the time grading the quizzes. All right, bye, Ziwei. All right, Team 5, Wei Xiang here says, for Farmville, TCP better? Data integrity. So you probably like games like Farmville. Do you play Animal Crossing? Yeah, if you do, then, and if you love Animal Crossing, you thought that growing these trees and flowers, you kind of, cultivated it with all your heart, right? So maybe TCP is better for players like that, really, really serious about this type of game. Why does interactive game need less throughput than video? Oh, interesting. Yeah, Catfish, that's a very good question, right? Interactive game sounds like multimedia and interactive real-time multimedia. You know what? Game data is not quite like videos, audios. Game data, you see, a lot of times it's just a short message saying, there's a player going to location XY. So it's actually short text messages. Therefore, unlike audio video, you kind of need to convert from analog signal. Audio video, it's a very natural phenomenon. Electromagnetic waves, essentially, you convert them to digital bits and you try to compress such that you use as few bits as possible before sending it out on the network. But even that we try to compress, that's still a lot of bits required. But if it's just coordinate, two numbers, that's just two floating point numbers or two integers. Okay, the number of bits required much, much smaller. That's why game data requires less throughput. But you see that there's another kind of interactive game these days. Have you heard of Stadia? So this is actually a gaming service from Google. I think NVIDIA as well as Microsoft, they also are working on something similar. So instead of sending game data, okay, or having players sending your game actions to the server and server sending back additional messages to make sure your client program renders certain graphics, okay. Stadia, NVIDIA's new gaming service, what they do is you send, okay, bye Yuntong. You send your comments to the server. NVIDIA, Google, Microsoft, they use their graphic cards to render the game images. And they stream the game images frame by frame, much like how the videos are being streamed. For this type of game, the throughput requirement will be higher. You see? So it has something to do with exactly how the game data are sent, how the game graphics are generated. In the first case, a server message back, the client program is rendering the graphics. Therefore, you need high-end graphics card in order to have vivid rendering of the hairs under there's a breeze a flow airflow over, and your hair would flow a certain way. You need a high-end
graphics card to do that. But you see that the graphics cards are all very expensive these days. So these companies are thinking another way of streaming or allowing online games. I am still not clear about how public and private key work for server and client. Okay, that's a great question. This has something to do with so let's first establish how public key and private key work. Okay, so one question at a time. So let me answer Keke's question first. So I hope that the idea of public key and private key is clear to you. All right. So client and server are essentially two ends of communication. Okay. Each of client and server will have their own pairs of public key and private key. So server will have public key, private key. Server's public key, private key. Client would have client's public key and private key. Yeah. So this key pair is unique for each end host. Okay. So with the private key and public key for each end host. Yeah, bye, Justin. Go. This is the bell for the next lecture. So go catch the next lecture. And the students staying are just, to follow up with the questions. You guys can always come back to the video to catch up. All right? Just go. Don't worry. Okay, bye. So that's it. This is client and this is server. All right? So this is much like Alice, and this is much like Bob in the scenario I show in the video. Okay. So for these two to communicate, of course, the simplest form is instead of using public key, private key, they just send the share key to each other. So this client here, Alice, is requesting to send message secretly. So Alice can, of course, send the share secret key to Bob, right? And then Alice and Bob can use the share key to encrypt data afterwards. But you see that share key, as it's being sent, if there's someone eavesdropping, then that secret key is out. And of course, the guy eavesdropped the secret key can decrypt all the messages Bob and Alice are sending. You see that the traditional way of sending data secretly has a hole. It's not big, tiny, just the initial sending of the secret key. Okay, so this is where public and private key comes to help. I don't know if you have taken cryptography yet. When I was teaching Introduction to Computers, I actually teach public and secret key, the basic ideas, and I also give a quiz to show you that it's not that hard to generate the key pairs. Use number theories, and the formula is public, so one can generate key pairs easy. It's just that if you want to reverse engineer from public key to private key, it's really, really hard. I see, that's why. So Keke, perhaps I can share, I'll generate a video talking about public key and private key, and then give you a quiz and you can work on it. And let me know whether you know better what public key and private key, how they work. Okay, then it might be a little bit easier to explain how we address this issue, right? The initial sending of the shared key, that's a hole. That's not secure. Okay, so in order to be secure, and we send the shared key insecurely. So let us do that. Let's take it offline, and I'll generate a video so that you can follow. Otherwise, this might take a little bit longer. Okay, because what I explained in the video is just, I assume you know already. If Alice here encrypt with Bob's public key,
only Bob's private key can decrypt. So when Bob encrypt a message using Bob's private key, everyone can decrypt using Bob's public key. So it's a key pair. If you encrypt with one, you can only decrypt with another one. You cannot decrypt with the same one generating the message. So it's quite amazing. I'll show you an example, then you will be convinced that will work. So that pair is specific. It's not like, randomly you pick a key or two. No, it's not like that. Okay, you have to generate them. There are formulas you use to generate them to ensure that if you encrypt it in private key, you decrypt in public key. If you encrypt in public key, you decrypt in private key. Okay, let's let me attend to Catfish's. Okay, great, thank you, Keke. Let's come to Catfish's question. Can an app use multiple sockets or protocols? Yes, you may. In fact, you may. In the PAs, we use just one. But one can definitely create multiple sockets and connect to multiple servers at the same time. It's just adding another line. The same line you use to connect to one server A, you can just add another line you connect to server B. You just change the IP address. And you can specify for server 1, you use UDP. For server 2, for server B, you use TCP. But you need to make sure that server A allows TCP. Server B allows UDP. Catfish, that's a very good question. Unfortunately, we don't have a slight complex application scenario for the PAs. But after you start working on PA3, I think by PA4, you know that it's actually doable. You can actually try creating a scenario yourself and try to write a client with multiple servers, connecting simultaneously to multiple servers. Okay, good. I guess that's it. Does a socket have a port or multiple ports? That's a very good question. A socket has only one port, but a program starting 2 sockets can have 2 ports. Does that make better sense? So in a way, a program can create multiple sockets or create multiple connections, and each of the connections uses 2 different ports. Yeah, and you know what, Catfish, you're asking a key question. Nowadays, the network programs are all multi-threaded, meaning that we're doing many things at the same time, or seemingly at the same time. So we actually maintain multiple connections. Tomorrow, I'm going to talk about HTTP. HTTP browser maintains multiple connections to the servers a lot of time. Multiple sockets to the servers a lot of time. Okay, good. All right, certainly lots of questions. I guess you guys are picking up more when Polly play the videos faster. That's very interesting. Well, let's keep on with the experiment, and bye Catfish, bye Cuckoo. Good, that's end the stream.